Hi everyone, so in this video we are going to be recording a bit of a kind of an introduction to the acids and bases topic, which is the final topic of Unit 1 in National 5. The topic is going to cover a few things that we've done previously in S2. So we'll be looking at pH and the pH scale, we'll be looking at universal indicator and the colours that the indicator turns and so on. And we'll be kind of drilling down a little bit more into what a base is and how a base and an alkali are kind of similar and how they're different. And also we'll be looking at what happens when acids and alkalis or acids and bases react together and what's made. So in previous years we've met this pH scale and the way that we kind of measure and test acids and alkalis and different chemicals that we might use in a lab. So using something like pH paper or using universal indicator, you would be able to test different solutions and be able to figure out the pH that they have. And so the relationship, just to kind of refresh our memory a little bit, is that an acid is any solution with a pH less than 7. So we don't say between 1 and 6, we say less than 7, because pH can be whole numbers, it can also be decimals and things. So 6.5, for example, isn't between 1 and 6, but it's still an acid. So anything below 7 is an acid. 7 exactly is neutral, and then anything above 7, so anything on the upper side there, is going to be classified as an alkali. So the idea of using the pH scale and using an indicator like pH paper or universal indicator, which is the liquid form of that indicator, is that it tells us a little bit more about the chemical than just is it an acid or is it an alkali. It can help us to tell the difference between something that is very acidic, something that is slightly acidic, and something that is again very alkaline or slightly alkaline. So our three sort of warmer colours, our reds, oranges and yellows, are acidic colours when we're talking about universal indicator. Now it's important to note here that not every indicator is exactly the same, but universal indicator is the one that we kind of base a lot of this chemistry on, because it can tell us if something is an acid or an alkali or neutral, and it can tell us how acidic or alkaline that chemical is. So it ranges from red through to yellow. You then have your sort of greeny blue, turquoisey colour through blue and then into purple for your alkaline, and then your green is the one in the middle that's going to be your neutral solutions. So one of the things that you're going to have a bit of an idea of, and we're not saying that you have to memorise this list that we're about to show you just now, but something you should have a bit of a handle on are some common examples of the types of acids and alkalis that you would find in the house. These chemicals are not just things that are found in science labs, they're found in your everyday life. You've got acid inside your stomach, for example, and you've got alkali inside things like batteries, for example. So it's about knowing where these things exist in our everyday lives. So we'll start off with a list of common household acidic substances, and you can see from the top there that you're going to be talking a lot about fruits mainly, foods, but particularly our fruits. So apples have generally a pH of around about 4. You've then got things like lemon, which is a citrus fruit, orange in there as well, grapefruit. These are quite sour in taste, and that sour kind of taste is quite common as a sign of an acid. Acids are kind of characteristic by their sour flavour. So obviously the more acidic something is, the more sour it's going to taste. So your apple at pH 4, it's not particularly acidic compared to a lemon at pH 2. But in there you've also got a really common example that we would use a lot when we're talking about these types of questions, for example, would be to be thinking about vinegar. Okay, vinegar is one of our really common examples that you see being used a lot in questions and things as a common example of a household acid. So vinegar. So as well as having household acids, we also have some common household alkalis. So here we have a list of common alkalis you would find at home that range from things like baking soda and toothpaste, right up to things like soap and even bleach. Your sort of household cleaning products, quite often oven cleaner and things like that. The really strong household cleaners would often usually be an alkali. One of the questions that we kind of move on from thinking about from S2 going into the acid section here in National 4 and National 5 chemistry is to think about where do acids actually come from, how do acids actually get made. Now we cover it a little bit in S2 when we think about an environmental problem called acid rain, and the simple answer is that acids are produced when a non-metal oxide dissolves in water. Now what we mean by non-metal oxide is simply any non-metal from the periodic table which is then bonded to oxygen. So a really common example would be in your fizzy drinks. So in a glass of Coke, for example, you've got carbon dioxide, which is CO2. Now that's dissolved in water, and when that's dissolved in water, it produces what you would think is carbonated water or fizzy juice. Well, it's actually carbonic acid or hydrogen carbonate that it's forming. So here we can see a bit of a summary of that point. So acids are produced when non-metal oxides dissolve in water, and there's a little word equation here on the screen and 3 examples. You've got carbon dioxide forming carbonic acid. You've got sulfur trioxide, which dissolves in water to form sulfuric acid, which is our H2SO4, and then phosphorus oxide, which dissolves in water to form phosphoric acid, it's called. Now we don't expect you to learn all these examples off by heart, but we do expect you to know this line at the top of the screen here, that acids are produced when non-metal oxides are dissolved in water. Now as we start to think about what sets National 4 and National 5 apart in the knowledge that we have to have, we look here at a table of some common acids that you would find, not necessarily household, these are more sort of laboratory based ones. But what we've got here is a group of acids. We've got the oxide that they come from. Now you'll notice at the bottom that not all acids are actually formed from an oxide. What we're trying to get across here is that if you have a non-metal oxide and it does dissolve in water, you will make an acid. But that doesn't mean to say that all acids come from non-metal oxides dissolving in water. But that's certainly one way in which they're formed. Hydrochloric acid, which is a really common acid, one you'll be familiar using in school, is actually from the gas hydrogen chloride. Its chemical formula doesn't change, it just becomes a solution. So when the gas hydrogen chloride dissolves in water, that actually makes hydrochloric acid. So what we're going to look at just now is the chemical formula of the acids that we have here on the screen, because the thing that really sets National 5 apart from National 4 is going to be thinking about these ions that are in the acids, and we're going to spot something as we go through this, and that's going to really be our first big National 5 outcome of the acids topic, is about an ion that's present in every single one of our acids. So hydrogen carbonate or carbonic acid, our first acid, its chemical formula is H2CO3. Now we've previously looked at the writing of ionic formulae, which is where we look at the ions that are present. So hydrogen, okay, forms the hydrogen ion. So we've got 2 hydrogen ions present in this, and we have a carbonate ion, which is our CO3 2- ion. And as we go through the rest of these, we're going to spot a bit of a common theme. So sulfuric acid is H2SO4. Again, we've got 2 hydrogen ions, and we've got a sulfate ion. I just realised that my finger's scribbling on the screen here as I write. We've also got phosphoric acid, which is H3PO4. So we're going to have 3 hydrogen ions and a phosphate ion, which is PO4 3-. We've got nitric acid, which is HNO3. We've got the H plus, we've got the NO3 minus. Hydrochloric acid is HCl, again H plus and Cl minus. And now here's one that we met in Unit 2, which is ethanoic acid. So ethanoic acid is CH3COOH, remember the COO group from our carboxylic acids. Well, again, it's going to form the hydrogen ion, and this time it's going to form what's known as the ethanoate ion. So ethanoic acid forms ethanoate, which is our COO minus at the end there, the CH3COO minus. But what we should quite clearly and quite easily be able to spot here is that every single one of these acids has something in common. Every single acid contains the hydrogen ion, and that's a really important point, okay, and that leads us to a conclusion. Really simply, all acids contain the H plus ion. Now that is called, if we're going to name it, very simply, because it's a positive ion, we don't have to change the name at all, it is called the hydrogen ion. Okay, and the hydrogen ion being present is a really key indicator that something is an acid, and we'll come back to that idea after we've introduced alkalis. So back in S2 we would look at a definition of an acid as being a solution with a pH less than 7. And that's still true, that doesn't change. But now, because we are starting to understand a little bit more about ions, and we're starting to understand a little bit more about the ions that are present, we can actually use this sentence on the screen just now to give us a better definition of an acid. And really it comes down to the presence of these ions. So what we do is we compare everything to pure water. Okay, pure water is our kind of baseline that we're looking at. And if you take water and then you take another solution, and that solution has a greater concentration of hydrogen ions than the pure water, that would be an acid. Okay, so that leads us to our new definition, our National 5 definition of an acid, which is any solution with a greater concentration of hydrogen ions than pure water. Okay, so they have effectively an excess of hydrogen ions. So here on the screen you can see the next idea that we're going to have. I quite like this section because a lot of the chemistry that you learned in S2 when we were thinking about acids was the idea that acids and alkalis were opposite from one another. So acids react with alkalis and they neutralise each other. They're at opposite ends of the pH scale. And it's quite fitting that the way that they're produced is the kind of opposite as well. So we learned a few moments ago that acids are produced when non-metal oxides dissolve in water. Well, here we've got a really simple idea that alkalis are produced when metal oxides dissolve in water. So here, instead of having things like carbon dioxide or nitrogen dioxide, we've got instead magnesium oxide, calcium oxide or zinc oxide. So these are chemicals that dissolve in water and produce this metal hydroxide type compound, and the metal hydroxide compound is the alkali that's being produced. Now there's one thing I would like to draw your attention to, which is to think about page 8 in the data booklet. And the reason I want you to think about page 8 in the data booklet is because on that page there's a table that helps you to work out whether a chemical is actually soluble or not. And that's a really important idea, because this isn't just about metal oxide being added to water. The key word here is dissolve. Now you'll sometimes get an example of a question where it will be something like which of the following chemicals dissolves in water to produce an alkali. There may be 2 metal oxides in the list, but what you'll find is that in that list only one of them will be soluble according to page 8 in the data booklet. And there's a little clue in the question, if you get one of those in an exam, which it'll actually say you may wish to use your data book to help you, which is a little clue that what we're thinking about is page 8 and we're thinking about solubility. So bear that in mind as we go forward. So just like we had a look at the table of acids and the non-metal oxides that they come from and the ions that are present in them, we can do the same for our alkalis. And you can notice here there's a really subtle change, a really small change in the name of the metal oxide and the name of the alkali that it forms. So sodium oxide simply becomes sodium hydroxide. So it's a really small change, but potassium oxide will become potassium hydroxide. And exactly the same again, calcium oxide will become calcium hydroxide. Just shows that I can't talk at the same time. Hydroxide. I can't even write and talk at the same time either. I can't think and talk at the same time. Next we've got the formula of our alkalis. So our sodium hydroxide, we can use our SVSDF method that we've met before. Sodium and hydroxide. The hydroxide ion found on page 8 of your data booklet is OH-, so that's sodium hydroxide. Next we have potassium hydroxide. We then have calcium hydroxide, where there's 2 hydroxides present. And then lastly, ammonia, which is really important actually later on in the course during Unit 3, forms a solution called ammonium hydroxide, which involves 2 different ions, both of which are found on page 8. The ammonium NH4 and the hydroxide OH ions coming together there. So when we look at the ions that are present, this time Na plus and OH minus, K plus and OH minus. We also have in here Ca2 plus, which means we're going to have 2 of our hydroxide ions, OH minus, and then our ammonium NH4 plus ion from page 8 in the data booklet, and our hydroxide ion from page 8 in the data booklet. And what we should be able to see here is, again, we've got a common theme. We've got another commonality between each of these, which means that we can then make another conclusion. So this time, instead of them all containing the same positive ion, they all contain the same negative ion. Okay, and that ion has a name. It's in the data booklet. Because it's negative, its name will change slightly. The ending of it would be "ide" or "ate", usually if it's a negative ion. So in this case, it's the hydroxide ion. Okay, and that's a really key part of this course, is that our acids contain our H plus ion, our hydroxides contain our OH minus, our hydroxide ion. So just like with our acids, we can take our knowledge of S2 in our acids course that we've done before. You know, an alkali is any solution with a pH greater than 7. It's still true. That doesn't go away. It's not wrong or incorrect or half-truth or anything like that. It's completely true. There's just another version of our definition, a slightly more detailed version. Because we know a little bit more about ions, we can now say that an alkali is a solution which has a greater concentration of hydroxide ions than pure water. So again, the comparison is made between the chemical we're looking at, the alkali in this case, and pure water. Okay, and the difference between the two is that the alkali contains a greater concentration of the hydroxide ion. Okay, now that's the end of this video for today. Have another chance to go through this video if you need to revisit any of the points. Don't be frightened to reach out and speak to your teacher if you're finding anything difficult, and be sure to make sure that you're creating a set of notes by using the little notes symbol that you can see here at the bottom of the screen, which tells you whenever there's a slide from this presentation that needs to be added into your notes. Okay, have a great day.